Hello everyone. We are from Department of Mechanical Engineering of Maharaja Agrasen Institute of Technology. Today, we'll be presenting our project, the Solar Thermal Adsorption Refrigeration System or STAR system. This is a passive compressor-less refrigeration setup that operates using solar energy, ethanol, as the refrigerant. It uses activated carbon as the adsorbent and produces cooling during the night, driven purely by the solar heat collected during the day. The goal of this system is to demonstrate a clean, sustainable cooling method that can work even without electricity, ideal for remote and rural areas.
The STAR system is based on the adsorption refrigeration cycle, which works using two processes, adsorption and desorption. During adsorption, ethanol vapor is captured by the porous surface of activated carbon. During desorption, the same ethanol is released when the adsorbent is heated by solar thermal energy, which superheats the vapor. The system operates in two main phases. At night, adsorption occurs after generating a cooling effect. During the day, solar heating causes desorption, regenerating the adsorbent. This makes it an intermittent refrigeration system, cooling at night and heating during the day, completely driven by renewable solar energy.
Now let's understand the setup and components of the STAR system. The STAR system consists of 5 main valves. Valve A and E on the evaporator side, which is also our receiver. Valve B after the evaporator, before the solar collector. Similarly, valve C just before the solar collector, and valve T after the solar collector, before the condenser. The setup also consists of 2 vacuum ports in order to evacuate the air from the setup. One is from the condenser side, VPC, and another is on the evaporator side, VPE. Now let us understand the functioning components of the STAR system. This is the receiver and evaporator. Its main function is to absorb the heat from the environment. This valve E is also the expansion valve used to cool the refrigerant coming from the condenser. Our next most important part of the system is the solar thermal collector. This is a flat plate based collector which absorbs sunlight and converts it into heat, which is then transferred onto the refrigerant. The next component is the fan cooled condenser. This is a heat exchanger which releases the heat of the refrigerant and transfers the liquid refrigerant back into the evaporator. We are creating vacuum in our system. For this, we will first create vacuum in the evaporator section. Before switching on the pump, we will ensure that all the ports are in the desired positions. The valve A should be in open condition. Valve B also should be in open condition. We will close the valve C and open vacuum port E. Now, after switching on the vacuum pump, we will operate the vacuum pump till minus 700 mm of Hg pressure is reached. Now we will close the vacuum port E and switch off the vacuum pump. To prevent the backflow of ethanol, we will close the valve B. Now let's move to our solar collector section. For creating vacuum in the solar collector section, we have to ensure that valve D is in the closed position. Now, let's move to valve C and open it. And after switching on the vacuum pump, we will open the vacuum port E. Now we have reached our desired pressure, that is minus 700 mm of Hg. We will close the vacuum port E and switch off the vacuum pump. At last, we are going to create vacuum in the condenser section. To create vacuum in the condenser section, we will switch on the vacuum pump and open valve port C. Now we have reached to our desired pressure and created vacuum in the condenser part also. So we have successfully created vacuum in the whole system. Now let us understand the working of the star system. During night time, the receiver or the evaporator contains liquid ethanol, which is a refrigerant in this case. This liquid absorbs heat from the environment and converts it into vapor continuously. This valve is closed to prevent backflow of refrigerant, and the refrigerant flows through valve A, which is opened, through the valve B and into the solar collector through valve C, where it is adsorbed onto the surface of activated carbon. This adsorption phase of the vapor refrigerant into the carbon present in the tubes is completed during the night. Once all of the refrigerant is adsorbed onto the tube surface, we close the valve C to prevent its backflow. And during daytime, when there is direct normal sunlight onto the receiver, the sunlight is absorbed by the collector and converted into heat. This heat is transferred onto the activated carbon, which desorbs the refrigerant and superheats it within the pipes of the collector. It is important to note that during this phase, valve D is closed to prevent flow of the superheated vapor into the condenser. Once daytime is over and the vapor is completely superheated and desorbed from the surface of activated carbon, valve D is opened to transfer that superheated vapor into the condenser, which is fan cooled in our case. This fan cooled condenser dissipates all of the heat of the refrigerant and converts it into saturated vapor. And this saturated vapor is then transferred through this line into valve E, which is opened, and valve E expands it and converts it back into liquid refrigerant, which is transferred into the evaporator, allowing the cycle to repeat.
The STAR system can be used in rural and off-grid regions for vaccine storage, food preservation, and milk cooling. It is especially useful in areas with limited access to electricity, as it runs entirely on solar thermal energy. With further optimization, it can also be scaled for portable cold storage units and climate-resilient cooling solutions.
To sum up, the STAR system offers a clean, sustainable approach to cooling. It eliminates the needs for electricity, compressors, or synthetic refrigerants, using only ethanol, activated carbon, and sunlight. Thank you for watching. We hope this project inspires further innovation.